So this is the final experiment we're going to show in a video format. So we're back to the 10 megahertz transducer. We've got the coupling gel on the test block. We've got a different test block here, a 35mm thick steel block. Everything else is as we've had. I've adjusted the settings on the Panametrics for the specific experiment, just to so that what you see on the screen is clearly illustrated. And so if we power on and we make sure that we get good acoustic coupling, you can see there's an excess of coupling gel here. This will help when I'm going to scan the test piece in a minute or two, so we'll be able to see in different areas of the test piece what the actual signals look like. So we can see here that we have the main bang on the left hand side, and then we have the back wall echo or reflection occurring further in time. So we have 2 microseconds per division. So we have effectively, we can move our cursors. So main bang's happening here. So we've got 1, 2, 3, 4, 5, almost 6 divisions. So it's approximately 12 microseconds before we get the first echo. We can, again, as we've done previously, we could reduce the time base, and we can see the multiple reflections as reverberations of the ultrasonic energy within the test block. This is as a back again to the original scenario. So it's a 35mm block. You should be able to work out the time difference, the time of flight associated with that from the 6mm per microsecond value that I mentioned previously. So if we consider that we're actually in a situation here where we don't just want to find the back wall signal, but we're looking for any artifacts or features in a test piece, what we would do is we would move the test piece around, and we would be looking at the signals that we acquire. And there's some surface roughness on this test block, so we do need some good coupling gel in order to manage that process effectively. So we can move the test piece around, and as we're doing that, so I'm moving this with my left hand, and you can see the signals are fluctuating just as we get a variety of coupling, but effectively that the signal or the time of flight, the arrival time of that echo does not move. If we continue to move around, I think it's a point where we start to see another echo coming in here. So this is 2, 4, 6, approximately 7 microseconds. And if we move around here but carefully, we actually can that can then become the predominant signal, and we can see that the signal that we were receiving associated with the back wall echo reduces quite significantly. So there's various explanations for this, which I'll explain in a minute. So this is the back wall echo. As we're moving along, we start to see an indication of something happening around 7 microseconds. So what's happening there? So effectively what we're getting is we're now getting 2 signals that have been returned to the transducer with different path lengths, and we can use this information in order to understand what's going on within the structure, so looking at features or flaws or defects. As we move along, we can see that the signal at 7 microseconds actually starts to become the predominant one, and then there's at one point where actually the back wall signal effectively reduces to 0. So my interpretation of this would be that we have a defect within this structure, which is at a depth within from the surface, which is sort of less than the back wall echo. Effectively, what happens is the transducer at one point is partially over the defect and partially still getting reflection from the back wall. So that's where you see the two echoes as we would have here. And then there's another point in the system where we are almost entirely, or we are entirely over the defect. So there's no signal coming from the back wall at all, and then we can pass through the other side, and the back wall becomes prominent, and eventually we go back to just seeing the back wall from the component on its own. So from that we could actually scan this surface, and we could map out these signals, and that would give us an indication of the scale, and so the dimensions of the defect in terms of the scan dimensions that we do on top of the transducer. So for example, what we would have here, so if we were scanning along, so we can use that information where we collect every data point, and we can use that to assess the actual overall lateral dimensions of the defect, and then we can use time of flight. So we can use this 7 microseconds, and we should measure it more accurately, but we should use that 7 microseconds to determine the depth at which that defect is actually located. So I've now reverted back to the location on the block where the transducer is half over the defect and half over the back wall. So you can see from the markers that I've put on here, so the distance between the excitation signal and the signal from the defect, so that's the one at roughly 7 microseconds, is 6.87 microseconds. And if I move this out, then we see that the time of flight associated with the back wall is actually 11.85 microseconds. So we can use that information to determine the thickness of the material. But if we know the thickness of the material, then we can actually use that to calculate more accurately the speed of sound in that material, and then a knowledge of the speed of sound and the time of flight to the reflection at roughly 7 microseconds from the defect will allow us to work out the depth. It should be apparent that this signal that's coming in here is the second reflection associated with the defect. So as we move on, we can see that is the back wall is removed completely. We still see the reflections at 7 and at 14 microseconds. So if we have the situation where we're half on and half off, and then we were to move the time base, we get a very, very complicated chain of echoes associated with this particular component. Primarily, we'd be looking for we can use this information we use this information in a variety of ways in order to determine an image or some way of representing the internal features of this particular defect, this particular sample. So we're just finishing off here by showing the other side, the underside of that steel block, and you can see quite clearly a circular defect of significant depth, which we can estimate from, or we can calculate from using the data from the time of flight that we measured on the oscilloscope. So that's these series of training videos complete. I hope you've found them informative. and we'll be following up on any questions you have in an interactive lab session, which will go over some of the same material, and you'll be able to hopefully get more familiar with the basic ultrasonic measurement instrumentation, albeit from a virtual perspective. Thank you.